Okay, it's recording. Okay, let's get started. Um, this will be. So, did I turn on my camera? Looks like my camera's not on. Okay. Can you see my face? No.
No,
Okay. Yeah, I guess my camera's not on. This one. I'm using a different link today.
yeah, I can see you now.
Okay, good. Okay, so welcome to the last two classes of system security this semester. Before we get started, several announcements. First, there will be a final exam on December 14th, 7:15 to 10:15 in the evening. And the format of the final exam will be similar to the midterm exam. There will be several challenges, not necessarily four, I'm still debating how many. So there will be several challenges. There will be no multiple choices questions this time, just the challenges. And the challenges may include what you have, what we covered at the first half of the class, and it will definitely cover what we have in the second half of the class. To prepare for the challenges, what you're supposed to do is to get us through your homework, uh, go through the challenges, the examples we have in the class. That's how you get prepared. And there will be no in-class CTF. Instead, there will be a take-home exam. And this take-home exam is obviously not online. The final exam is like online. You will do things uh, uh, during that time period, and you cannot communicate with each other, and you have to turn on camera. The take-home exam will be a little bit different. There will be several challenges as well, but those challenges will be a little bit more difficult. I will try to release that as soon as possible so you can start working on those. So the final exam will only be 100 points, same as the midterm exam, but the take-home exam will be 200 points. And there will be other multiple choices questions as well. So as soon as I release that, you can start working on those. Okay, so today we are only talking about one thing, is the Meltdown attack. The next week, the last class, we will talk about uh, Spectral. So, um, so some of you may heard the Meltdown and Spectral, which are very famous attacks, vulnerabilities that are related to the hardware, affecting many different CPUs. And the Meltdown Spectral were discovered 2018, like 2 years ago. And most of the CPUs we are familiar with, like the Intel ones, ARM ones, probably some ARM-based, they have this vulnerability. So no one knew this vulnerability exists, and this is attacking some very fundamental security properties of hardware of CPU. So when this type of attack was first released, uh, first discovered, people were like, "You must be kidding me, right? How is this possible?" Um, so those two vulnerabilities were discovered by several researchers. Some of them were actually several teams independent with each other, but they published papers together. Those two papers, one was published in Unix Security, maybe another one was published in Oakland, I don't remember. Uh, but there is a website, it's a meltdownattack.com. So if you click in, you can see Meltdown and Spectral. Maybe there's a link to Spectral. And there is a CVE related to Meltdown as well. So the vulnerability was reported probably late 2017 or early 2018. The paper was published a half a year after that or something. Yeah. Um, so these are very serious um, problems uh, when they were discovered. And because they are hardware vulnerabilities, they are also related to cache side channel attack. That's what we discussed last week. Um, they were considered very difficult to fix because they're hardware problems. Some of the hardware problems you can fix by updating the hardware firmware, like the Intel. So, Phil, could you please mute there? I can hear some noise here. Yeah, good. So, some of the hardware problems can be fixed by updating the microcode of the CPUs, but some of them are difficult or just impossible to fix uh, at the hardware layer. That's why some of the mitigations to this are still at a software layer. Um, for the latest CPUs, I'm not sure actually what's going on. So last week I showed you my CPU. If I do a LS CPU, and it shows it's not really vulnerable to Meltdown attack, but it is vulnerable to Spectral. And last week I was trying to do Meltdown on my new computer, and it didn't work. So, but it probably will work on most of your computers. So anyway, as a homework this week, you are trying to do this attack. Um, no matter it works or not, you will do the attack and just show me the results if it works or not. Okay. So some Meltdown basics. So the Meltdown vulnerability allows attackers to read arbitrary physical memory uh, from an unprivileged user process. So this is a fundamental property for the CPU, for modern CPU and for the OS, right? If there is an unprivileged user-land process, that process should be only able to read the memory that mapped to its process, and it has permissions to read them. Not only mapped. There are memory mapped to the user process, but the user process doesn't have the permission to read those. So this is basically achieved by hardware. First of all, the memory management unit, and also the operating system will utilize memory management unit to uh, to enforce this kind of a policy, right? So this is a very fundamental security property offered by modern CPUs. Actually, let me think. Very, very long time ago, probably starting from 83, 86, or let's just say 386. I think it's starting from 386 or maybe at least 486. So the first Intel CPU, the famous ones, is 8080, then 8086, then we have all kinds of 86, right? So I think it's at least from 486 that should be in the 70s or 80s, maybe 70s. They start to have this protection mode, and they have MMU to separate unprivileged and privileged code. And since then, we have this kind of hardware boundaries to protect the kernel from being read, write by a user application. However, after that, we adding more and more optimizations to make CPU faster and faster. And some of the optimizations turns out can be exploited to break that fundamental security property. And Meltdown uses one of those uh, optimization features, which is called out of order instruction execution. Spectral use out of order and also use speculative execution, which we will talk about next week. So Meltdown utilizes this feature to leak data at any physical memory address uh, to a user process. And the way to leak data is carefully, smartly designed to use a cache-based covert channel. So there are two different things. First one is the out of order execution um, where trigger this kind of problem. Then after the problem is triggered, to actually leak the data, we also need a covert channel cache-based to do that. And there are software-based solutions to mitigate or help mitigate meltdown. For example, Linux, they have the kernel level address-based name-order randomization to make things difficult. The attacker needs to know the address of the secret, make things a little bit difficult. Okay, so before we talk about meltdown, we will talk a little bit about what is this out of order execution. So basically, this is something you learn from your computer architecture class. I'm not sure who is teaching computer architecture in our department. And I guess it's not required for everyone. So some of you may never took this class before. So on this slide, we have a typical CPU, a 5-stage pipeline CPU. So the white boxes here, each of them represent one stage in the CPU pipeline. So at a classical RISC CPU, there are 5 stages. So F means fetch, means fetching the instruction from the memory. D means decode. E means actually executing that instruction using some execution unit. And there could be multiple different execution tasks, right? Some of the tasks may need multiple cycles. For example, the integer add just need one cycle for the execution unit. Then the integer multiply will need 4 cycles of that unit. Then there is a float point number multiplication, which needs 8 cycles of that unit, that execution unit. So here, each box represents one cycle. So the F fetch means, so since there's only one box, we consider it will only take one cycle, and there is a fetch unit, which is a hardware to do that. And decoding, also there is a decoding unit, which takes just one cycle to decode the instruction. So after that, we may have memory access unit to access memory, and also a write back unit to write results back to the memory. So usually, not usually, I mean, long time ago, the CPU, so from the software developer's point of view, from even system developer's point of view, when you look at, we have been looking at a lot of assemblies, disassemblies, instructions. From our point of view, when we were debugging code, we think those instructions execute one by one, okay? That's what we believe. And that is what the CPU, we believe the CPU is doing, and at least from the software perspective, that is what the software expect. However, under the hood, things could be much more complicated. So one of those features is called out of order execution. So the old one is, if the instruction just execute sequentially, this is called in order execution. And the problem of in order execution is some instructions may be dependent on other instructions. some instructions may not be dependent on previous instructions. So if an instruction is dependent on a previous instruction, then the previous instruction has not finished, then this instruction has to wait. However, in order execution, all other instructions after this instruction has to wait. So we are actually wasting a lot of time for those CPU units. Let me show you one concrete example here. Let's say I took this from some computer architecture class slides. Let's say here we have two different pseudocode, right? And this is a RISC architecture, so we have many registers here. The first one we have multiply R1, register 1 and register 2 and save the result to R3. Then we have AND R1, R3 to R3. So you can see that the second instruction AND R3 and R1 to R3 is obviously dependent on the first one, because the output of the first instruction R3 is used as the input of the second instruction. It's independent. So the second instruction has to wait for the first one to finish. Otherwise, it cannot do any calculation. It doesn't know the value of R3. However, the third, fourth, and fifth instruction are different. They are not really related to those two instructions here. The third one is and R6, R7 to R1. And of course, they have to write the value back to R1. But besides that, the other four stages, like fetching, like decoding, like execution, has nothing to do with the previous instructions. But if the first instruction takes 4 cycles, so there's a multiply. Let's assume it takes 4 cycles here. We have to wait. Okay, that's in order execution. So because of that, we are not fully utilizing all the CPU units. Okay, some of the units are not used during some cycle, which means we can do better. Well, the extreme case, if we push CPU to the to stretch the CPU to its best capacity, what we should do is we use all its units inside the CPU in every CPU cycle, right? So if we're not using some of them, then we are wasting them, which means we are wasting time. Of course, we're not necessarily wasting energy, right? Oh, interesting. We may waste energy as well, because we spend more time in execution anyway. Okay. So the idea to solve this problem is something called out of order execution or dynamic instruction scheduling. So basically, we're not talking about to solve the problem at the compiler level. Well, because look at this problem. You probably can solve this problem at the compiler level, somehow make them do not block, rearrange the instructions. For example, let's say, oh, this one, we cannot put this one in the front. But there may be something you can do at a compiler level to do optimization. But here we're talking about something directly at the CPU, inside of the CPU, not really at a compiler level. Okay. So the idea is to move the dependent instructions out of the way of independent ones. Okay. So the second instruction is dependent of the first one, but all others, they are not dependent on any of those, right? So instead of blocking at the second instruction, we will keep execution or other instructions. But we do that internally. We do that inside the CPU, okay? So we do that inside of the CPU, and only when it's really our chance to execute the fifth one, then we say, oh, is the result we calculated before still valid? If it's not valid, we just discard that. Maybe we need to execute this again. If it is valid, then we just use the one we pre-executed. So it's like we are taking a chance. The CPU is taking a chance to pre-execute something out of order and try to make the program run faster. And it works. This is a very important feature that can make the CPU run quite faster than the inline in-order execution. Here we have another concrete. Yeah, let's just use this example again. We have these 5 instructions. Then we have two different. This is called the. What is this table called? I don't remember what this is called. A table called. Anyway, the x-axis means the cycles, the CPU cycles. That means this is the first cycle, second cycle, third cycle, that. Then the y-axis, so we read the x-axis start from here and go this way. The y-axis actually start from here, then go downwards this way. So this y-axis here represents different instructions. X-axis represent different cycles. So for example, the first F here means this is the first cycle of the CPU, and we are talking about the first instruction. Okay. At the first cycle of the CPU, what we are doing is we fetch the first instruction, and that's it. That's the only thing the CPU is doing in this cycle. The CPU has 5 units, remember. So the other 4 units are not doing anything. Okay. Then the second cycle, we have decoding. So the decoding module of the CPU, the decoding unit, is decoding the first instruction, which is integer multiply. However, the fetching unit of the CPU can also work, and it will fetch the second instruction. Okay. The third cycle of the CPU, we are executing the first instruction, which will take 4 cycles. Okay, that's why there are 4 E's. Then we decode the second. The decoding unit will decode the second instruction, and the fetching unit will fetch the third instruction. However, at the 4th cycle, what we're doing, remember, we're doing in-order execution. The 4th cycle, the execution unit is still executing the first instruction. So the decoding unit cannot output the result to the execution unit, so you cannot reuse it. So obviously we assume there is no other buffer to save the result or whatever of the decoding unit. So the decoding unit cannot be used. It's blocked. And the fetching unit is also blocked because the decoding unit is blocked. So in the 4th CPU cycle, even though we have 5 independent CPU units, fetch, decode, execution, memory read, and write back, we are only using one of those units. We are wasting the other 4 units, okay? Then the 5th cycle, the same thing, the 6th cycle, the same thing. Only we get to the 7th cycle, we finished executing this instruction. Then there will be a memory access, which takes 1 cycle. In this case, I mean, this instruction doesn't really have any memory access, but for simplicity, we will just use those typical 5 RISC cycles. So right now we have the memory access unit running things. So the execution unit can run the second instruction, and the second instruction only take 1 execution cycle. Okay. Then the decoding unit can do the 3rd one. The fetching can do the 4th instruction. Okay. Then after that, another cycle, we have the write back. We have so in this cycle, we actually have all 5 CPU units running. Okay, we're not wasting anything. And you see that if we just do in-order execution for these 5 instructions, it will cost us 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the whole thing will be 16 cycles. Well, those 5 instructions will cost us 16 cycles. In computer architecture, there's a very famous book. I think it was authored by a previous, maybe computer science department chair or dean at CMU. So he has a book, John Henry, I don't remember his name. So the book is called Computer Architecture, a Quantitative Approach. So, so in that book, there is a definition, the metrics to measure the speed of CPU is called cycles per instruction. Cycles per instruction. So basically, it's average for each instruction how many cycles it's used. Okay. So in this case, we have 5 instructions and we used 16 cycles. So it's so the cycle per instruction is as high as 3 point something, right? 3.2 in this case, which is bad. Actually, sometimes you can make the cycle per instruction very low, even lower than 1, if you fully utilize this. So in this case, even you fully not utilize, you cannot achieve 1. But I think there are some features, some CPUs can do that. Okay. So to optimize this one, what we can do at the CPU level is this thing called out of order execution or out of order dispatch. So the same instruction with the out of order CPU, what will happen is the first one, for the first instruction is the same, right? It's fetch, decode, for execution, the memory access, write back. For the second one, the same thing. However, the difference is here. The difference is here for the third instruction, because the third instruction doesn't really need the result of the first 2 instructions. Okay, there is no reason that the third instruction should be blocked here. Instead, the third instruction after fetch, it will decode. It will be decoded. After it's decoded, the CPU realizes it doesn't need to wait for the result of the first 2 instructions. Then we can execute this. Maybe we have another execution unit, maybe to do that. Then we have write back, we have memory access. Then the problem here is the third instruction can say we're writing the value back to R1, right? Because we're writing the value back to R1, we cannot do this after the first 2 instructions, because the first 2 instructions they use the R1 as input. So it may influence the previous 2 instructions. That's why we wait a little bit. Of course, this is just a high level picture. Sometimes it doesn't have to wait this long to do that, right? Then the fourth instruction can say it's not blocked by anyone, even though it has 4 cycles for the execution. You can say that for this one, we are fully utilizing for a lot of cycles. We are utilizing many units. Of course, for some of the units, we might have 2 copies, right? So to execute those instructions, those 5 instructions in this out of order CPU, we only need 12 cycles. So the cycle per instruction is only 2.4 something here. So that's basically the very high level idea of out of order execution. And this out of order execution is not really a new feature in modern CPUs. It has been there for 30, 40 years. And only 2018, people realized that. Combine this with something else, we can do something amazingly dangerous, which is Meltdown. So next, we are going to look at the Meltdown example. So for this example, we are using the seedlab. We are using seedlab, sorry. So if you already started your homework, you notice that I asked you to download the seedlab virtual machine and run those there. For this lab, you should also download the code from seedlab. So why I don't have internet? Okay. So yeah, it's here. So you just go to seedlab, then go to this new version, then go to system security labs. And there are only two labs here, Meltdown and Spectrum. So this week we are going to do Meltdown. So what you need to do is, there is a good description of this. This is like I don't know, 15 pages something. So you need to read this. So we already covered a big part of this. You also need to download the source code, which is here. Then put that in your virtual machine. The virtual machine doesn't have the source code. I have the source code here downloaded. And let's see what we have. There are several different source files. The cache type is just like what we did last week to show a basic cache side channel attack. A flash reload is the example we showed last week, which is a flash reload cache side channel attack in one process. There's a make file. The make file doesn't. The make file is only responsible for generate the kernel module here. Then we have a kernel module, which is meltdown kernel.c, which has a secret we are supposed to steal. Then there is a meltdown experiment. Then this is the first version of this attack app. And then there is a meltdown attack.c, which is a more advanced version of this. Unfortunately, it doesn't work on my computer, but it should work on most of yours. But we can still take a look at this and learn a lot of this. Let's start from the kernel code. Meltdown kernel.c. You can see that this is basically a kernel module, or in some cases, we just call it a driver. If you want to develop a kernel module, you develop a driver. That's the terminology for Linux or Windows, the same thing. They all call it a driver. So the book, Linux driver development, Windows driver development, basically talking about not necessarily developing a driver for a physical device, but it could be just developing some general kernel modules. Okay. I remember the book Linux. Do I have it here? Oh yeah, I do have it here. If you can see it here, I have this Linux device driver book, and in this book, I remember the first 2 or 3 examples has nothing to do with a physical driver, a physical device. The driver basically is just a kernel module that do some computation, whatever. Okay. So this one is also a kernel module. When you develop a kernel module, you notice that it's different from application. In application, say application, you have a main function, right? That is the main function as we analyzed in the first half of the class. The main function is actually called by the some start underscore start or underscore start main, those kind of a C library functions. But in the kernel, when you are running things in the kernel, you don't even have C libraries. Okay, that's the first thing you need to realize. You don't even have a C libraries. The libraries the functions you are using there are just the kernel functions. For example, you notice that this one, we're trying to print something, and the print function we're using is not printf, right? In C programming, you use printf, but this one is printk, okay? So this is not a C library function. This is a function in the kernel that kernel modules can call. And this function has the same syntax, the same arguments as printf. However, they're different things, okay? So this function will write a message to the kernel message buffer, and you can use D message to say the message buffer. We will say that in a minute. And you notice that this function, there's no main function, right? There are several functions here, but there is no main function here. But like all other programs, there should be an entry point. There should be an exit point for you to, when you want to this program to quit, you should give the program a chance to clean up the mess it creates. That's why the Linux kernel provides two macros. I'm not sure if those are functions or macros, maybe macros, for you to tell the kernel or also compiler what is the entry point of this module, what is the exit point of this module. And you just use module underscore init, module underscore exit to tell the compiler. Okay, in this case, obviously the entry point is test underscore proc init, and the exit one is a text underscore proc clean up, right? So let's say, okay, so this one is our entry point. So this function is our entry point, which means when this module is loaded into the kernel, this kernel module is loaded into the kernel, this is going to be executed. This function will be executed in the kernel mode. Okay. So what this function does is it will first print out one line. Secret data is at address. Okay. And the secret data is actually a global variable here. Okay. So this is a secret we are trying to steal using Meltdown. And obviously this secret is in a kernel memory because this is kernel module. Then we have a lot of pointer. We use vmalloc here to get something, get some heap area for us. And we're not using malloc because malloc without the v. Malloc is a C library function. So here we don't have C library, so we use a v. V here stands for virtual. It guarantees to give you a continuous virtual area. There is also kmalloc here, but here we're using vmalloc. So you can see there's a vmalloc here. We're asking 8 bytes of data, 8 bytes of space on the heap, the kernel heap. Then we put that return address to the secret buffer, which is just a pointer here, static char secret buffer. Then after that, this module, we will create an entry in the proc file system. The file system proc is for different, basically it exposes a lot of things from the kernel to applications. So applications can just open this. So we are creating a node there called the secret data. So after this, in the file system, you will have something proc secret data. So let's take a look because I already installed this. So secret. Yep. Since I already installed this module, you can see there is a proc secret data node under that proc file system. Okay. So if we just read it, so if we do a cat, then we are just reading it. It doesn't really do anything because this one doesn't give us any data. Okay. So this is how we create this node in this file system. Then this function just return. So this is the init function of this module. And the exit function of this module is just to remove that node from this kernel, from this proc file system. Okay. Then for all those kernel devices, usually we talk with them using a standard file-based, let's say, interface. Okay. So this interface has what? Has open, read, llseek, those things. Open, read, write. Okay. So what is open? What is read? Or what is write? Those are the system calls we use, right? So when you open a file, you use a system call open that file. When you open a socket, you use a system call open that socket. When you want to read from the file, you use a system call read. You want to write to the file, you use the system call write, right? However, that's actually an abstraction. Why is that? Because those file descriptors, they map to totally different physical devices, physical entities. For example, open the std in, which is like the terminal, is totally different from open the file in your hard disk. Those are totally different operations. But so far, like we have been programming so far, we are using the same interface, which is just open. Well, we have been open std in, we have been open a file. You didn't think about they are two different. They are actually different entities with different characteristics. You don't need to, for software developers, you don't need to think about that. That is because the Linux kernel, the model actually treat everything kind of like the object-oriented programming. And it's like how C++ do things, right? So in C++, you can create something called class. The class means the type of this data structure. And this type is associated with different operations on it. And the operations may have standard names. The names of those operations are the same interface. However, under the hood, each operation is different depending on the type of it. So the Linux kernel, even though it is not developed by any very high level programming language, C++, Java, or Python, they have this philosophy there. They have this object-oriented programming philosophy, okay? So every entity there, they can be represented as a file, can be indicated by a file descriptor. And they will handle the same names of interfaces, like open, like read, like write. However, under the hood, the developer of those modules defines what means by open. That's what we have here. So open, in this case, open on this file actually means calling the function test underscore proc open. And this is a function developed by the kernel developer. So you can do whatever you want, okay? It doesn't have to be even, somehow semantically related to the word open. Doesn't have to. But of course, that would be bad practice, but it doesn't have to, okay? Or let's say read doesn't have to be read, doesn't have to give you something. In this case, we can say the read system call here, not technically this is when you do a system call, read system call on this proc secret data node, this function read proc will be executed. And you can see the implementation of this function here has nothing to do with reading anything back, right? That's why when we do a cat here, it doesn't give us anything back. Okay, what the read function does here is just copy the data address. No, copy the data. So those 8 bytes of secret, copy that from its original place to the new location on the heap. That's basically what it does. And the purpose of this in this program is just to utilize this secret, so the secret can be injected into the cache. Okay, under the hood, it will be injected into the cache. And the open one is just a standard open, so it doesn't really matter. Okay, that's it. That is the kernel module. So the kernel module has two things. One is it has a secret we want to steal, which is seed lamps, 8 bytes of secret. That's what we want to steal. Okay. Then it has a read interface exposed to us. But doesn't, when we do that read thing, the kernel will copy the secret from one place to another place. And the goal of that is just to bring that secret into the cache. That's it. Other things are just a standard, not really that important. So you will use the make file to compile this kernel module, and this is the kernel module's make file. You can see that this make file actually will call other make files to build the module. After you build the module, you will use, so all of this is documented in that NAP description. So don't worry, you don't have to remember what I do here step by step. And you can also use the install module instruction to install the module into the kernel. Of course, you need the sudo. You need a sudo to do this. So after you install this, like I said, after you install this, the init function will be executed, which means this print k function will be called, and it will not print out things to your screen terminal. Instead, you can use the dmessage utility to find out the message. So this is basically a lot of kernel modules. Giving out some information to the log, and you can see. So for this Meltdown kernel module, we didn't really specify the license. So they didn't specify a license. So the kernel have a warning that this taints the kernel, which doesn't really matter here. Okay, so if we do a message, then we just do a grab secret. We can say this is a message the Meltdown module gave us. So the secret has address this. Okay, so if we go back to the code again, you can say this function will just print out the address of the secret. That's what we need in this case. That's a virtual address for the secret. Okay, so that is the first step of this attack. We try to, of course, in a real world attack, you are not trying to inject a kernel module to inject some secret there. You are trying to find out some secret in the kernel you want to steal. But that secret, you need to the address in advance through other methods. And another challenging thing is you need to somehow get those value of that address into cache first. If you don't get those value into cache, the chance of successfully extract all of those data is actually not very high. Okay, that's why in the stamp they designed this specific one, so it has a much better chance to extract the secret. So obviously, if we want to directly read that memory location, now we know what is the memory location. But if we just directly read that, we will not be able to get that because we're running an application. We try to read the kernel memory address, it will just give us a segment fault. We're not supposed to read there. The MMU will trigger the fault. That's why they also have a very nice. They also have a very nice example of exception handling. So we will go exception handling.c. This is a small application. Let's say so. This is an application. So there is a main function, and you can say at the main function we can have what? And the main function we can specify the kernel data address. We can put the address we just have, put it here. Then we just execute this, and it's supposed to give us and try to access that location. Then we will just trigger the segment fault. However, what if we don't want to have a segment fault? We want to handle this gracefully. Then, so usually when we do that in terminal, we have the segment fault print out. That's because our application is not handling segment fault. In that case, the kernel will handle it. But we can choose to handle that gracefully. So instead, what we can do is we can, so the segment fault is like the kernel will send out a signal to the application, and that signal is called seg, which stands for segment violation. Okay, so we can register a handler there using the function seg to register a handler, and the handler we're using is in this case is catch segment fault. Okay, and this program also uses set jump and long jump. I guess some of you probably used the set jump and long jump before. If you haven't, just Google it. What is set jump, long jump? The implementation of set jump or long jump is complicated. It's architecture and also system dependent. Some of the implementation might be a function. Some of the implementation might be macro. That really matter. Different architecture will be different, but the C library does has that, which means for different architectures, the C library will implement set jump, long jump differently. Did we talk about set jump, long jump in the class? So any of you are here? Did we talk about it?
I don't recall.
Oh yeah. I guess I didn't. Yeah, I think I prepared something for it, but yeah, I think at some point I prepared a set jump, long jump, because set jump, long jump also have this. There is a code pointer in the set jump, long jump mechanism, and that code pointer can be overwritten. Then it can be used to return to arbitrary shellcode or whatever. Right? So if you just do a man set jump, yeah, it will tell you how to use set jump, long jump, and the set jump, long jump. They have a cousin called the seg set jump and seg long jump. So this one basically is used to handle signals. Okay. And the signals we're talking about here is basically, for example, this one is a signal sending from the kernel. So what this code does is it set up a signal handler, which is this one. Then it will set a seg set jump. So this seg set jump is basically saving the current state of the program. It will save the current state of the program to this buffer. The buffer is called a seg jump buffer. It will just sit there. So notice that this is a little bit weird, right? So in C programming, when you want to change something, you want to change a variable. Obviously, you want to save something, you have to change that variable. When you change those variables, you have to use the address of that variable, not just the name of that variable, right? So this doesn't make sense. That's because this probably is not a function. It's most likely to be a macro. So if it's a macro internally, it can get in the address of it instead of just using this one. Right. Okay. The second argument here, I think it doesn't really matter. What matters is the return address, return value. When you are actually saving things, saving the state of the process.
I'm
Yeah,
sorry.
go ahead.
It doesn't couldn't isn't in C the so the static sig jump buff, that's just a buffer, right? Like an
Yeah.
array. So
No.
I
Buffer is not necessarily array. We don't know what it is in this case. It's our own data structure. Yeah.
because you said we're because I thought it might be a pointer already, so maybe if it's a pointer,
So
then it might be a function, I guess.
some implementation I saw before, obviously this buffer has all kinds of register values. You need to, because basically that's what you are saving, right? So save all the registers. But if you do not use this, this will be on stack. So you will put that object onto the stack. That doesn't make sense, right? Yeah, so you should put the address on the stack so you can change the global variable. So basically this is a global variable. But if you do this, if this is really a function, you're pushing the global variable onto the stack, then whatever you're changing is that global, is that the argument on the stack, not the global variable. That's what I'm saying.
Okay.
Yeah, make sense?
Yep.
Yeah, so most cases, those are macros, not really functions. So this one, if this function returns 0, then it is the first time you are setting up, saving the state. Okay, later, if something bad happens, later, if you actually later you can return to this place. You as a developer, you can return to this place by calling that sig long jump. When you call this sig long jump, you are guaranteed to return here with the state of your program restored. Okay. The only difference is that time the return value of this function will not be 0. So this is like all the system calls, for example, like fork, right? When you do fork, you will create 2 different processes. One process will has guaranteed to have the return value 0. Okay, and another one will have the PID. We'll have the PID of the, I don't remember which is parent, which is, but use that. We can separate which process, then because you create 2 different processes, which process you are in. Here is a little bit similar, but we're still in one process. We just use the return value of this to distinguish if this is we are saving the state of the program or we are storing the states of the program. Okay, so if it's 0, then we are saving. So this is the first time we run this. Then what we're trying to do here is we will access that kernel address. And this will generate the segment fault because this application is not supposed to access that kernel data. Okay, this is application. That's why we have a printf, and this one will show us printf blah blah blah, right? But this statement should never be executed because whenever you execute here, you should trigger the segment fault. So you will skip this one. Instead, what will happen here is when here you will trigger that segment fault, then the kernel will send the segment fault signal to the application, and the application will handle that signal by itself because we set it up the handler before. Then the function will call this catch segment fault function, and this function doesn't do anything else, but just return to the place we saved the state. And this time it will restore the state like we just set up the signal. However, the return value will be different. Instead of going to this branch, we will go to the else branch, which will gracefully print out memory access violation. Then after this, print out program continues execute, the return. Okay, that's it. So this is basically an exception handler that you can handle those things. This example is very simple, but obviously you can do many other things. Instead of print out this, then exit, you can do other calculations. So this is a little bit similar to at other high-level programming languages, like even C++. We have a try-catch. Java, we have a try-catch. You can catch those Java. What is the syntax for Java? I'm not really a Java programmer. Java probably is not try-catch. But there are exception handlers for Java. So this is at the very low level. At a C level, what you can do, like an exception handler. So the program will not be killed. Instead, it will gracefully exit in this case. Okay. So let's see what else we have. The next we have is the Meltdown experiment code. Okay. So the Meltdown experiment code. So this is a Meltdown experiment code, and this is also a user application. And if you run this one on your machine, you probably can steal the secret. And we're stealing the secret using, there is actually one test we can do, even if the big one doesn't work. Let's say, oh yeah, there is. Okay, let's go through the main function here. Okay, so what the main function does is, first of all, it will try to catch the signal segment fault. Then it will flush the side channel. This is exactly what we discussed last time. And the first time, it will just try to meltdown access that kernel location. If it generates, it is guaranteed to generate that fault. So let's go to the C version. So here I'm quoting the ASM version, but let's go to the C version. So C version, this is a meltdown. Okay, it has the address of that data, kernel data, the secret. Then what we're doing here is we're just trying to read that data. Okay. What is interesting is this line of code. Okay. So tell me what do you think will happen? Those two lines of code. What will happen? When we execute the first statement, what will happen?
I expect we would have gotten the segment fault that we would have from the exception handler.
Exactly. So when we execute the first statement, that will be segment fault. So do we really have a chance to execute the second statement?
No.
From software developers' point of view, that's correct. We don't have a chance to execute the second statement. But under the hood, inside the CPU, this is the tricky stuff. The CPU actually will execute. Well, not always guaranteed. There is a high chance that the CPU will execute the second statement because of the out of order execution. Because the second statement has nothing to do with, in this case, has nothing to do with the first one. So it probably will execute. Even if we change the second statement, for example, here we're using 7. Instead of using 7, we use kernel data. This one could also be executed because there are two things here. When we actually execute the first statement, we are reading a memory location we're not supposed to read, okay? Then what happens is first CPU tries to read that location to fetch data, and also the CPU try to check if we have the permission to read that location. And they do not necessarily happen sequentially, okay? They do not have, you will, as a software developer, you were saying it should happen this way. It should check the permission first. After the check permission returns, we will try to access that. The problem is it will be very slow because you have to do it sequentially. So what the CPU does is different. The CPU will do those two things probably at the same time. It will check if you have the permission to read that, and it will also read that data back, okay, at the same time. And if the check permission returns early and says you don't have the permission, it will kill the other operation. If the check doesn't return that fast, or the check does give you a yes, you have the permission, then the other branch keeps executing. And after that, the second instruction, the second statement here may also be executed. In this case, those two statements are not really related, but let's try. I think this one may work. Let's say, so we have to, I need to change this code a little bit. So if you have a older CPU, it should work anyway, but we can try this. We're doing this Meltdown experiment. So location here doesn't really matter because we're not really, it doesn't work anyway. So any kernel location will be fine. So here, let's say, we're calling this the C version of this. Then we just want to compare this, mark native, what else flags do we need? We need any experiment. So let's just do it with Meltdown experiment. Yeah, I think that's a flag we need. Ooh. Ooh. Okay. Got that. So now we have this Meltdown experiment program here. If we just run this program, what do we have? Let's see. What happens? We actually get the secret here. Sometimes, not always, sometimes. Right? This one was not working, this one was not working, this one was 7. Okay, go back to the source code. What's going on here? So this one supposed to generate the segment fault. So everything, it will generate the segment fault. So anything after this instruction is not supposed to be executed. So this line of code is not supposed to be executed, but obviously it is. It was executed, okay? It was executed, and the value 1, the value of this array location, this memory location, the value was brought into cache, okay? If you check the value of this array, which means if you check at the memory level, the value will not be +1 because the CPU guarantees that at the software perspective, it guarantees the execution is faithful, right? This one is not supposed to be executed. However, they made a mistake or they didn't think it's important. They didn't, when this one is executed internally in the CPU, it will not only influence whatever register of this, it will also influence the cache. And they made the mistake that they didn't reset the cache. So this one, we are going to, for example, there is memory, right? This thing array is a memory, and you are going to use all kinds of registers when you do this operation. And the register value could be changed. And those values will be rolled back to their correct value after this statement. The memory will also roll back. Actually, the memory didn't roll back. They were never written. However, they do not roll back the cache. So the cache is influenced. Okay. So which means that's why we use that flash reload approach. We get the secret 7. Okay. We're not supposed to get that. Does that make sense? So the flash reload is exactly the same as what we talked about last week. So so basically this statement is trying to bring the index 7 into the cache, and the reload which was executed after this one memory violation was trying to check if we have been loading something into the cache. And it's clear that at least 50% of chances we say that index 7 is loaded into the cache. Does that make sense? I'm not sure if I explained that well here.
Yes.
Okay, let's think how we can change this a little bit. Let's say 2. Okay. So every one of this we set it as 1, right? So after this, okay, we can do this way. We can change this a little bit. So let's say let's print out. So after this, yeah, let's print out. Let's just hard code the 7 there, I guess. Yeah, this one just hard code 7. We just printf d new line array 7 times plus data. Yeah, I think that's it. That's the address, right? So that's the array 7 times this data. Okay. So at the beginning, the value of that place is 1, right? So if this statement is executed, that value there should be 2 because it's a plus 1, right? That makes sense, right? Okay. So if we print out this at the end, if that statement is really executed, the value should be 2. So we are actually talking about a very interesting state, right? At instruction set higher level, that instruction was not executed. So when we print out this, the value of that will not be 2, it will be 1. But inside the CPU, it's clear that that instruction is executed because that data was brought into cache. And we confirm that using a flash reload to confirm that that data was brought into cache, right? Let's just confirm that at a higher instruction set level, this one is not executed. So let's do it down, Meltdown, experiment. Okay, you can see the value is 1. The value is not 2, okay? So the value is supposed to be 1. That's what software developers expect. So the CPU is faithful in that sense. The CPU is faithful to software developers. It's supposed to be 1, and I'm giving it 1. But under the hood, inside of the CPU, they actually brought that into the cache. They actually executed that. Okay, and that is a huge problem here. Okay. So what we can do here is, instead of fix that certain 7 here, we can just read that data, that character. Well, it's just 1 byte, right? 256 possibilities. We read that data, Then the next line we execute. The statement is array that data is 1 byte. It's called kernel data. Then it's kernel data times the page size, then plus 1. This line of code, this statement should never be executed, but the CPU will execute it, and it will not change the memory. However, it will bring that data into cache. Then we do a reload. Then we can figure out what is the value of that kernel data. Of course, this is a little bit probability is there, right? It's not always, it doesn't always work. But if you run this multiple times, 10 times on the same location, you probably can get it working 5 or 6 times. And it's clear what is the data. So here is like, because of this, there are several vulnerabilities here, obviously. The first vulnerability is the out of order execution is exploited to combined with the cache side channel to send out message from the kernel from any location to the user space. This is a very smart exploitation, and this exploited is just this simple, but it's just here. Does it make sense? Any questions here?
Seems good to me.
Okay. So in this source code, you will see that there are 2 versions of this Meltdown attack. One is the assembly version. One is the state code version. The only difference here is actually there are some moving and adding some fixed number to AEX. That's only because somehow if you keep parts of the CPU unit busy, the chance to trigger this is higher. That's just it. Yeah. So somehow I cannot get this working on my CPU, but you can try this. There are some people are talking about you may try to disable the mitigation at the that's a part I don't know right now what kind of security features this CPU actually has. Maybe they already fixed this problem, but for older CPUs, there could be, if you updated your Linux or Windows, there could be some software mitigation. And if you want to make this work, you probably need to disable some software mitigation for Linux, for Ubuntu. It's at the boot time, you can give it some parameters, arguments to do that. For Windows, I'm not sure. But you can do this in this virtual machine and use that Arc native to do that. So I cannot show you the demo, but I did show you the demo of this one. This one does work. I'm not sure why this one, because if this one works, I think I know why this one doesn't work. Oh no, not necessarily. For example, this one may not be mapped. So this one actually also require the kernel maps those address to the user space. So they can do the translation. So if it's not mapped, let's say this address we gave is a virtual address. If that virtual address is not mapped in this process, MMU page tables, then they cannot even do the translation. They don't know where that data is. The translation will fail. So it doesn't work that way in that case. So maybe that's the reason we cannot get it. Okay. So that is the Meltdown experiment.c. They actually provide another version of code called the Meltdown attack.c, which is basically the same thing. The only difference is they adding a loop there to try to access the location for 1,000 times and calculate maybe calculate the average uh, cycles for each index, so that will increase the reliability of this attack. Because you see that when we do that attack, there are chances, there are like at least 50, 60 times we get it right, then other 40, 50 times we do not get it right. And if we just run it 1,000 times, then the differences of those indexes for cache hit and cache miss will be much more clear. That's basically it. And also they have a trick in this code. You see that the trick is they actually open that and try to just try to open it. There is no read, right? Is there a read? Oh, there is a read. Oh, there is a read. There is a read. So the read will guarantee that the kernel will copy the data secret from the global variable to the heap. Guarantee that it's in the cache. The reason to do that is to, like I said, this is also a risk condition here. The CPU where when you execute this instruction eventually should trigger segment fault. But when you execute the instruction, there are at least two things. One thing is to check the CPU, the system will check if the current process has the privilege to access this location, and also try to retrieve the data from the location. Retrieve data from the location might be slower than checking the permission. It's hard to tell which one is fast, which one is slow, because everything of this is inside the CPU. Intel people, they can measure that. Outside it, we cannot measure that, right? But to increase our chance is we try to make the reading data part very fast. By doing that, we increase the chance that reading data is faster than getting the permission check result. So that's why they try to put the data into the cache. So when the CPU executes that, they try to read the data. They're not actually reading from the memory. Instead, they are reading from the cache. That's why it's fast, and it's a higher chance to beat the permission check. The permission check may also be and permission. Is it also cached? I'm not sure if TLS has the permission bit there as well. Because there is also TLS involved to translate that virtual address into a physical address to actually getting things. Yeah, I think to do permission, you have to do a page table walkthrough. So that will take multiple, that may take multiple steps. Yeah, talking to the page table. Okay. That's basically it. Even though it doesn't work on my computer, it should work on most of your computers. So I will send out, it will just follow the lamp instructions for Meltdown in this step. And the next week we will cover Spectral. I'm not sure if Spectral work on my computer now, but I guess it works. Any questions there?
A quick follow-up, Dr. Joe.
Sure.
I think what we talked about last week,
yeah,
is that the Ryzen architecture for at least maybe some of the contemporary CPUs seems to be resistant to some of the side channel things that we've talked about. In my homework, I think I witnessed that in real time.
Okay.
Is that going to be consistent for Meltdown as well, or is there a chance that it will not?
It could be, because you can clearly see that this one will rely on flash and reload. If flash and reload is not working, then this is not going to work.
For your machine, is this still the i7, or did you move to a different machine?
I'm still using the i7 machine I showed you last week.
Okay.
But I did do this test last year using my old IBM ThinkPad, and it worked. And that ThinkPad was like 2 years old. I got it in 2018, so definitely there's no hardware changes to defeat Meltdown and Spectre. That's for sure. There could be software layer changes at the Linux side, but yeah, no hardware change. Yeah.
Okay, because I think yours is a 10th gen, and my other machine is a 10th gen 5. But I noticed that on a native OS on the i5, the basic flush reload we did for the homework worked great. So maybe I'll migrate to that machine and hope for good results. Okay.
Yeah, try that because this is a really fun and it's not that hard to try because you are just moving the virtual machine. So move the virtual machine there, just install VirtualBox there. Yeah, it's not like it. Yeah, it's not like you have to set up a lot of things. Yeah, yeah.
Great, thanks.
Good. Any other questions? Yeah.
I had a question regarding our last homework that was our ROP second homework for return oriented programming. In that, for the practical part, we had to follow everything that we did in the class. So yeah, for that, I did everything. I prepared the shell code like we did in the class, and everything was working well. And there was no segmentation fault, but I wasn't getting the output. I wasn't the output wasn't printing, but when I ran through GDB, the Wolfo function was working properly. Like everything was going according to where it should be, but there was some issue. I don't know. There was some issue when I was trying to set a breakpoint inside the Wolfo. It was giving some segmentation fault in the main function. So
how about
yeah.
this? Yeah, I did get your email actually. I didn't have a
Yeah.
chance to reply yet. So how about we set up a time tomorrow I can help you debug this to figure out what's going on.
Sure.
Yeah. Any questions regarding today's class?
No.
Okay, then our stop recording now. Then we can set up.
Also, I had a question regarding the the logistics of the class. In the syllabus, it's written that we have a CTF coming up.
Actually, I don't have time to set up the CTF. It's not ready, and I don't even know what kind of cloud infrastructure we have. That department, okay. I didn't really go to the campus a lot this semester. So instead of a CTF, what we're going to do at the beginning of class, I said that we're doing a take-home exam.
Okay.
We will have a final exam, and also will be take-home exam. The take-home exam will replace the CTF. The take-home exam kind of like the homework you guys did, but it will be much more difficult. I'm trying to combine several things together, create several challenges there. Yeah.
Okay. Thank you.
Then I guess that's it for today's class. So see most of you next week. Then Gersimran, could you stay here for a little bit? Yeah.
Yes, sure.
Okay, let me stop recording.